So now let's ask the question, what are the different factors that impact the size of this window? And we want to be able to find the most optimal window for a series of target images to generate a novel image that gives us the best possible blend. So to avoid seams of any form, the size of the window that we want should be equal to the size of the largest prominent feature. So in this case, if you look at it, the results look good here, but we do know that this image does have some issues with this spot kind of feeling a little cut up. Well, if we had actually kept the window size big enough for this one, we would have actually done better. Similarly, this does very well for this because the window size is decent for this one. So in essence, what we need is we want to have a window that basically is equal to the largest prominent feature on an image. Another rule of thumb here is that to avoid any kind of ghosting artifact, where actually you saw in the previous image where some transparent spots were visible across the two images, we want to have a window that's less than or equal to 2 times the size of the smallest prominent feature. So take any small feature, we want to make sure our window is twice as big. So again, if this was the feature we wanted to make sure our window size is big enough for that to be able to kind of hide away and not have any ghostly artifacts. And again, you don't see any here. You do see it a little bit, but remember, we are only doing a kind of blending in this direction here. This is where some of the stuff we discussed earlier with Fourier transforms comes in. Remember this example where we looked at basically a synthetic image which has these bands going across the image at 45 degrees. If you were to compute the Fourier transform of this image, we would get this, which basically kind of now shows the frequency spectrum and the repetitious nature of this image. Among other things, this repetitious nature also gives us a sense of the scale of different features that exist in this image, and perhaps also the repetitions of these features. So in essence, this frequency spectrum is showcasing how big the features are in the sampling space and how we can actually take the sampling size of the signal to account for what we want to look at. Again, something you may recall we discussed in the last lecture. So using this, and by then doing any kind of specific frequencies to look at, either low pass or high pass or band pass, we can now actually look at specific frequency information within an image. So for example, I could just create a region and I would look at all of the frequency information just in that one and concentrate on just those to be able to extract the window size. And of course, this is just basically how I'm showing it. I'm ignoring all of the information everywhere else, but just here. So in essence, what we are arguing for here is we want to be able to start using the Fourier domain to help us extract optimal window sizes. Here I share with you some of the well-known methods how we can actually do this. For example, if the largest frequency of the signal was less than or equal to twice the size of the smallest frequency, that will help us be able to kind of look for the right window size. And the other thing to remember here is that the image frequency content should occupy 1 octave, that is, just be able to look at within the powers of 2 of the frequency signal itself, and that will allow us to also determine the window sizes of this kind of stuff. Again, these are theoretical foundations of how we want to do this. As we go on further, we'll learn that we actually can learn and model these things quite well to be able to do kind of blending that we saw in the example of the cricket field earlier.